Hello everyone, welcome back. In this video, we'll be looking at the last problem of this week's biweekly contest, number of strings which can be rearranged to contain substring. The problem is very interesting and can be solved using pure recursion or pure mathematics. In this particular video, we'll be looking at the mathematics approach because that's what will be helpful when constraint is on the higher side. Currently, the value of n is 10 power 5, but if the value of n is 10 power 18 or 10 power 9 for that matter, you don't have the liberty to apply dynamic programming or recursion in that case. So with that, if you are interested in dynamic programming solution, let me know in the comment section below. If there is enough interest, I am happy to make another video explaining that solution as well. So let's get started. The problem states that you are given an integer n. A string s is called good if it contains only lowercase English characters, and it is possible to rearrange the character of s such that the new string contains LEET as a substring. So if the string is LTEER, this is a good string because you can rearrange the characters of the string into something like LETR, where LEET is occurring as a substring of this string. On the other hand, LETL is not a good string because no matter how you arrange this, you will not be able to get LEET as a substring. The task is to return the total number of good strings of length n, and since the answer can be large, we have to return it modulus 10 to the power 9 plus 7. So let's take an example where n is 4. So if n is 4, we have all these 12 strings which are good strings. Basically, you can rearrange their characters and you will see they have LEET in their substring. So basically, because the length of LEET itself is 4 and we are allowed to make a string of length 4 always, so hence you can see everything, it is just a permutation of LEET itself. So in total there are 12 permutations of LEET and hence 12 strings or 12 good strings. So hope the problem statement is clear. Now how to solve this? One of the way that you might think of while looking at the problem directly is, why not something like this? Basically you want LEET as a substring, right? So LEET is of 4 characters, right? So what you can say is, okay, I will select 4 characters, any random 4 characters or 4 places, and I will use these 4 places to form this substring, or where basically when I will rearrange the string, I will ensure that these 4 places have at least one L, at least 2 T, 2 E, and at least 1 T, and I will be able to make LEET out of these 4 characters. Now remaining characters I don't care, no matter what they are. I can simply put anything here because I am certain that these 4 characters will help me in making the string good, right? So remaining n minus 4 character doesn't matter at all. So how many ways are there? You can say, okay, there are total n places where we can fill something. We have to select 4 out of those n places, right, for this substring thing, and remaining characters I can fill in any ways. So n minus 4 characters, each of them has 26 different possible choices. Basically this character can be filled with anything between a and z, right? Similarly you can fill anything between a and z here, here, and so on, right? So remaining can be filled in this many ways, and you can select 4 of them from the n characters, and out of all of them you can, so this 4 you have selected, let's say, so among these 4 you can simply rearrange LEET in itself. So basically you are saying you have 4 characters here. Now no matter, you don't care where L comes. L can come either here, L can come either here, or it can come here, or it can come here, right? So you basically are arranging LEET as well among these 4 characters. So how many ways? 4 factorial divided by 1 factorial, 2 factorial, and 1 factorial. Basically the frequency of the occurrences, which if you evaluate will come to 12. So hence 12 into NC4 into 26 power n minus 4. But this will not work. Though this looks like a good and correct solution, but this is completely wrong. This basically contains extra answer which will never be counted, or basically it will count something twice or thrice, or basically x number of times. Now I would strongly encourage you to pause and try to think if or why this solution is not correct. So hope you have at least thought about it. The reason is simple. Basically we are picking up 4 characters of our choice and we are saying we will be forming LEET from these 4 characters always, right? And rest of the characters we have made them free and said that they can be of their choice. So no one is stopping in filling up these characters with LEET as well. So see, you have a single string in which you can form LEET in 2 different ways, right? And because you can form LEET in 2 different ways through the same string will be counted twice in this particular calculation. Basically when you select these blue places, then it will be counted as one way. When you select this red as the 4 different places, when basically we are trying out every possible combination of 4 places, right? So when this evaluates to this 4 places, the same string will be counted again as a different way. So the same string is counted in 2 different ways, and hence this will over compute or extrapolate the answer. But and you can say, okay, then why not divide by 2 or something, divide by x. Let's figure out how many times it will extrapolate and let's divide it by x. But that x value is something which is hard to find. Why? Let's look at it. You can see this string, right? In this string itself there are more than 3, like greater than 3 number of ways to in which this can be counted in this particular arrangement. One possible way is when NC4 evaluates to this star positions, right? If you look at the star positions, we have E, we have T, we have E, and we have L. So LEET we have, right? Similarly, if you look at the circle positions, again E, L, T, E. So the crux is finding out how many times a single string is computed or is recomputed in this entire calculation is something very hard, and it is not easy to find out a mathematical equation for that. And because we are not able to find it in a forward way, let's try the reverse. In other words, we'll say we know there are 26 power n different ways to fill this n characters, right? Among these we will subtract something and that will be our answer. Now what you will subtract? You have to subtract all the strings in which there is no L, right? No L, Similarly, you have to subtract the ways where there is no E. Similarly, you have to subtract the ways where there is no T. Similarly, you have to subtract the ways where there is no EE, and so on and so forth. So basically, you have to subtract some of the things or all the ways in which the string will not contain at least one L, at least two E, and at least one T, right? So whenever you see this kind of equation, the simplest thing you can do is set theory. You can say, okay, I know I need to figure out all the ways in which I can form a string which doesn't contain either A or B or C. So in other words, which doesn't contain L, EE or T, right? So we have named these three sets as A, B and C. A denotes the number of ways in which a number of strings which doesn't contain L. C denotes number of string which doesn't contain EE. Notice not E, EE. Similarly, B denotes number of ways or number of strings which doesn't contain T, right? So now what we need to find out? We need to just find out the number of ways or number of string that doesn't contain either A or B or C. Basically, we need to find out this area, this inside this part. We need to find out the value of this, right? So let's figure out the value of A first, right? So what is the value of A? A is basically all the strings which doesn't contain L. So we have n possible spaces. We want to figure out number of ways in which I can fill these spaces such that none of them contain L. So everywhere I can put anything between A to Z except L, right? So every place has 25 different possibilities, right? So the value of complete A is simply 25 to the power n. So we have these many strings which doesn't contain L at all. In the same fashion for T dash as well, it will be 25 to the power n. We have 25 to the power n number of ways in a number of strings which doesn't contain T at all. Now EE is interesting. We need to figure out the number of ways, a number of strings which doesn't contain EE at all. Basically two E's, at least two E's. So in this we will have all the strings which doesn't contain E at all, that is 25 to the power n. These many strings doesn't contain E at all, but there will be some strings which just contain single E, right? So doesn't contain two E's. We want to avoid two number of E's, but there can be strings which just have one E in total, and those strings are still counted under C because they still don't have two E's. So how to figure out number of strings which doesn't have which just have one single E? So we have n places, right? We know that one E is there. Now where it is, I don't care. So we will just select one position out of this n. This position will be filled with E. Rest of the positions can be filled with anything except E. So rest of the position has 25 choices, and total we have n minus 1 different positions left. So in total we have n into 25 power n minus 1 different ways in which the string can have a single E, right? So these are the values of A, B and C. I think I reversed B and C, so let's consider this as C and let's consider this as B, right? So these are the different values of A, B and C. Now let's try to figure out the value of A intersection B. So basically we want to figure out this entire thing, right? But simply A plus B plus C will not give us the entire thing, because if you do A plus C, you can see this space is counted twice, so you have to subtract once. Similarly, when you do A plus B, this space is counted twice, we have to subtract one. Similarly, C and B, this is counted twice, we have to subtract one. So basic set theory, and then finally we will add this thing once because this is subtracted twice again, so this will be added once again. So we need to figure out A intersection C, A intersection B, and finally B intersection C. After all of this, we also need A intersection B intersection C, right? So let's do one by one. Let's say we are trying to figure out A intersection B first. Basically all the string which doesn't contain L and T. So A and B is L and T respectively. So we have to figure out all the strings which doesn't contain either L or T. So every string will just have 24 choices because they can't have L or T. So it can have anything else. So there it can have 24 different ways to fill. We have 24 different ways to fill this character. Similarly, 24 different ways to fill this character, and so on and so forth. So in total, this part is 24 to the power n. Right now, A intersection C will be equals to B intersection C. In other words, we are saying that number of string which neither contain L nor EE will be equals to number of string which neither contain T or E, because of symmetry, right? So let's figure out A intersection C first. In other words, we want to figure out all the string which doesn't contain L and EE both, right? So again, this has two parts. One, the string which neither contain L nor contain E. So all these string will not have L and EE. And second part is the string which contain just one E. Just one E but not contain L or second E, right? So just one E or no L or E, right? So let's figure out the first part where the string doesn't contain neither L nor E. So again the same thing, each of them has 24 choices without L and E, so 24 to the power n. Now the second part was just contain one E. So where does that E belong? I don't care. So NC1 is the total number of ways to select the position of E. Once we have filled up one position with E, let's say this position with E, now rest of the places I can't fill L and I can't fill a second E. So rest of the pieces still have 24 different choices. So 24 power n minus 1 is the number of ways. So this is the total number of ways in which I can create a string which doesn't contain L nor EE. So A intersection C will be equals to 24 power n plus n into 24 power n minus 1. Similarly, B intersection C would be the same, 24 power n plus n into 24 power n minus 1. Now finally, A intersection B intersection C. So you want to find out this particular area, the string which neither contain L nor contain T nor contain double E. So again two parts, the string which nor contain L, E and T. The second part is the string which just contain a single E, right? So let's do the both. So the string which doesn't contain L, E and T is the first part. So again each of them has 23 different choices because we can't put L, E and T. Others we can put anything between A and Z. So 23 different choices for each of the spaces. So we have 23 power n different strings which nor contain L, neither E nor T. Now finally we also want to find out the string which contains single E as well. So again position of E doesn't matter at all, so we just fill one space with E. Rest of the places I can't fill L, E or T, so 23 choices for rest of the places, and they are total n minus 1 different places. So again, A intersection B intersection C would be translated to 23 power n plus n into 23 power n minus 1. So if you just do a recap, this is what we have till now. So if we have this set A, B and C. A, the value of A is 25 power n, value of B is 25 power n, value of C was n plus 25 multiplied by 25 power n minus 1. Basically it has two parts, one which contain C, which contain just one E, and one which doesn't contain E at all. So this n into 25 power n minus 1 is the number of ways which contain single E, and rest 25 power n is the ways which doesn't contain E at all. Similarly, A intersection C is just 24 power n, neither contain L, neither contain T, and then A intersection B and B intersection C are equal. Basically the string which doesn't contain L and double E, the string doesn't contain T and double E, so they both are equivalent to this. We derived that, and finally A intersection B intersection C will be equal to this. Now finally you can now figure out this entire value, A intersection A union B union C, and the value for that would be A plus B plus C minus A intersection B minus A intersection C minus B intersection C plus A intersection B intersection C. If you are new to this, basically this is simple set theory. If you do A plus B, you are counting this thing twice, so you subtracted this once, right? Now with just these three values you have this piece with you, right? This let me just make it bigger. So we have this piece with you. Now once you do C, once you add C, you have added this thing twice again, so you have to subtract this again. So we subtract C, A intersection C again. Now once you subtract A intersection C, you can also see this part is also twice added, so you subtract B intersection C as well. Now see, you subtracted this thing twice, once here and second here, so you just added this thing once again, which is A intersection B intersection C. So that's the basic formula of A union B union C. Once you figure out, this will give you the number of strings which neither contain L, nor contain T, nor contain E, or any of those. So what our task was to figure out the number of ways which doesn't contain, number of strings which doesn't contain substring LEET. So we'll simply subtract 26 power n minus this thing, A union B union C, and that will be our final answer, which is number of string which contain LEET as a substring, right? So hope this entire thing makes sense. If you have any doubts, feel free to rewind the video and watch that particular section. All the timestamps are there in the description down below. Now the final piece, you can see calculation of each of these involve 25 to the power n or something to the power n. Now in the starting of the video I said that n can be anywhere between 4 and 10 to the power 9, right? So how to solve for this constraint? So the thing is, you want something to the power something where the power is actually on the highest front. So that you can achieve by using fast exponentiation, which is nothing but a simple trick with binary numbers. I've explained that multiple times in the channel. Let's just look at it one last time. Let's say you have to figure out x power 12. One way is to just multiply x 12 number of times and do a modulus at the end, right? That will work, but that will require you to iterate over the power number of times, and in our case power can be very huge, up to 10 raised 9. So what you will do, you will say, okay, I will not multiply x these many times. Instead I will say, okay, I will use this thing, x power a plus b is actually equals to x power a multiplied by x power b, right? So I will use this technique to figure out the value of x. So in a way, to figure out the value of x power 12. So in a way, I will divide 12 into some number of summations, x1 plus x2 plus x3 all the way up to something, right? Now this things is something I already have calculated values for. Basically I know what is the value of x power x1, I know what is the value of x power x2, so I can just simply multiply them to get the final value of x power 12. So that's the basic idea. Now what this x1 x2 x3 would be, you just have to have enough number of them so that you don't end up multiplying. So one way is x1 is 1, x2 is 1, x3 is 1, so that is simply multiplying x 12 number of times. That is not efficient. So we just have to make sure that we have enough balance between what x1 x2 x3 are, so that we can compute them efficiently as well, and then finally we have small number of them as well, because if this summation is very huge up to xn, let's say if n is very huge, this solution will not scale. So we need to make sure that n is under control, and whatever the value of xi's are, we already know x power xi's beforehand. So the simple trick is use binary numbers, just represent 12 in binary format, and that's it. So we already we can compute the value of x power xi's beforehand. So we'll say x power 2 power 0, which is x power 1, which is simply x. Now x power 2 power 1, which is simply x square, right? X power 2 power 2, which is x power 4. Now what, to compute x square, you can simply multiply this part twice. Similarly, to compute x power 4, you can simply multiply x square by itself. Similarly, to compute x power 8, you can multiply x power 4 by itself. So notice, with just one multiplication you are able to compute the next values, right? Similarly, you can compute everything up till, let's say, 2 power 30, right? Now you can represent this 12 into binary format and pick the ones which comes in 12. So if you represent 12, it will come as 1100, right? So you can simply pick these values from here and multiply them. So this is 1, this is 1, so you will pick this value, multiply them, and that will be the value of x power 12. So you just have log n number of these xi's, and all of these will be calculated in just one iteration. So overall you will do log n number of operations to first compute this array, and then do log n multiplications to finally compute x power n. So hope this entire thing makes sense. Now if you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself. Next we're looking at the code. The code is straightforward, nothing fancy here. This is just the fast exponentiation function, which is giving you a power b. Now as discussed, the answer is 26 power n minus something. So what is this something? We first do a plus b plus c. So what is a plus b plus c? If you look at this, 25 power n minus 1 is common across all of them. So if you take this 25 power n minus 1 common, this will be n plus 25. Here you will be left with 25. Here you will be left with 25. 75 plus n. So 75 plus n. Similarly, if you look at this piece, so you have 24 power n, 24 power n minus 1. So 24 power n minus 1 is common, and this occurs twice. So 2n plus 48 plus 24, which is 2n plus 72. And finally the last piece is 23 power n plus 23 multiplied by 23 power n minus 1, so which is simply 23 power n minus 1 multiplied by n plus 23. So if you do this and finally subtract it from 26 power n, you will get the number of strings which are actually good, or which contain LEET as L, at least one L, at least two E, and at least one T. So hope this entire thing makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and to subscribe if you haven't already. And I will see you in the next one. Thank you.